Good morning, good evening, folks. Welcome to Machine Learning Foundations, Module 3, Session 1. So this morning, our speaker is going to be Parul Pandey, and she's going to sort of dive deeper into machine learning. So without further ado, let me hand it over to Parul.
Hello, everybody, and welcome to this Machine Learning Foundations module. And we're going to dive deeper into the supervised learning with H2O. So my name is Parul, and I'm a data science evangelist here at H2O.ai. I was also the instructor for the ML module in the AI Foundations course. And this current module is sort of an extension to that course because we learned about the theoretical concepts of supervised learning there. And here we're going to get into hands-on. So let's begin. So just to give a quick overview, we have, this is the third module. And before this, we have touched onto the basics of ML with respect to data wrangling and feature engineering. Today, we're going to do the first session, and there are 3 more sessions into this module where we will tell you how to use H2O and Rival SAI to do classification, regression, and even unsupervised machine learning, for instance, clustering. So what can you expect in this session? We'll go over a very quick recap of the supervised machine learning concepts. We won't dive deeper into it because I've already covered them in the AI fundamentals course, but I'm just going to touch upon them just to keep the flow of the session. Then I'll give a brief introduction to the H2O-3 platform. I'll tell you how you can install it locally on your systems and then get started. And then we're going to start with the case studies that we have. So a very quick note on the quizzes and hands-on exercises. So they will be posted in the site just few hours after the session gets over. And there'll be handouts which will explain how you have to proceed and perform the hands-on exercises. And I highly recommend you all to actually go and start coding and just to get a kind of complete knowledge and understanding of how things are happening under the hood. So let's start with the concept of supervised machine learning. Now, as I told you, I had already covered a major chunk of this in the AI Foundations course. So if you want to have a quick review of it, we also touched upon reinforcement learning there. We're not going to discuss about that in this session, but you can just go back and get a quick recap of the whole thing. So supervised learning is primarily divided into regression types and classification types, depending upon the type of variable that you want to predict. Now, if you want to predict continuous variables like sales of a company, profit of a company, interest, which are continuous, then such kind of problems are referred to as regression problems. On the other hand, if your motive is to actually identify category, whether a person will churn or not, whether this email is spam or not, so distinct categories, such problems are referred to as classification problems. So whereas in regression problems, we try and create a regression line, in classification problem, we try to differentiate between the two classes, and the better the differentiation, better is our model's performance. Again, these are some of the examples for classification, which you must have encountered. Finding a category, whether your tweet is positive or negative, for social media analysis, whether a person is going to default on a credit card loan or not. On the other hand, for regression, we predict a numerical value, like predicting profit for a company after a few months, or the sales in summers, and interest on for a bank. Now we know what kind of problem we are going to do. So to solve a problem, to solve a machine learning problem, we need to have an architecture, a suite of libraries and algorithms that we use. Today we're going to use H2O. So H2O is an open source architecture, and the name of the company is also H2O.ai, and so is the name of this architecture. Now H2O, in H2O, we can ingest data from multiple sources, as you can see on the left side of the screen, from HDFS, from S3 buckets, even locally, even from SQL. And all this ingested data goes into the compute engine, which is like the core. So there you load data, you do exploratory data analysis, you do feature engineering, supervised, non-supervised modeling, training, and predictions. All this thing takes place in this H2O compute engine, which is written in high performance Java. And this actually makes it very fast. From here, you could export the model in form of a Mojo and use it on many different infrastructure. But then, since it's written in Java, do we need to know Java to use it? No, because it has APIs in most common programming languages like R, Python, and it even has a web interface. So if you do not want to code, you can simply use the web interface, and with click and run, you can actually train a complete machine learning model, see the metrics, visualize the important parameters, and also make predictions. So if we look at some of the salient points of H2O, it enables distributed, that is multi-core and multi-node implementations. Most of the algorithms which are used in the industry have been written in H2O also, are available in H2O, and they are written in high performance Java. And like I said, the APIs are available in all the common programming languages. You can also easily deploy your models once created because they are written in Java. So this makes it very convenient. And this works on major platforms like Hadoop, Spark, EC2, Kubernetes, even your laptop. Now let's look at some of the machine learning features of H2O. So H2O has plethora of machine learning algorithms, right from supervised to unsupervised and also deep learning. It also has an automated machine learning algorithm, which sort of automates the entire machine learning process. We are going to cover about H2O AutoML in the third session. So make sure you mark those dates. It also has the ability to impute, scale, and normalize your data. And if your data has categorical variables, it can auto one-hot encode them. So it takes care of those. There is an early stopping available. So for instance, if your model's performance isn't improving, so you can early stop your training process. This saves a lot of time and memory also. Again, cross-validation, grid search are available in H2O, and you also have a lot of metrics, which we are going to see very soon. So this is just a high-level architecture from accessing H2O, then all the familiar algorithms in H2O. Like for instance, you have XGBoost, you must be knowing about that. So we also have its implementation in H2O, and then it's distributed and in memory compute. Okay, so now we have some idea about H2O-3. Let's see how we can install it on our own systems so that we can get started. And the installation process is very, very seamless. So H2O has an R package, and that you can install from CRAN, and also has a Python package that you can install from Python package installer. So you can just install the following dependencies and then just write pip install H2O for Python package. But if you want to look at all the other available options to download, you can go on the download page and you can see you can download and run from the command line. You can install in R. You can install in Python. You can install in Anaconda Cloud on Hadoop. So all the instructions are very clearly laid out. You can just go to this page and I will provide the link in the references and you can download this. So now we know what H2O is. We also have installed it on our system. Let's start and use it. The problem that we're going to do today is the loan mortgage problem. One of the very common problems that is used to demonstrate the supervised machine learning, but it also is important because this is actually a real life use case. So a lot of machine learning today is used in financial sector with the banks, and this makes it an apt problem to be solved so that you can get an idea of what kind of data sets are available. So the common workflow of machine learning is you need to ingest your data, you do some analysis, you do some feature engineering, you create models, you train your model, and then you ultimately explain it and you predict. So we are also going to follow the same path. The data that we are using is called Freddie Mac. Now this data comes from Freddie Mac actually. And what is Freddie Mac? So the Federal Home Loan Mortgage Corporation, FHLMC, is also known as Freddie Mac. It's a government-sponsored enterprise. And what it does is it buys mortgages on the secondary market, pulls them together, and then sells them as a mortgage-backed security to investors in the open market. It's in US. And what it did was last year, as part of the effort to increase transparency, it made the loan level credit card performance data open for anybody to use it. And this data set is from 1999 to 2019, which is like 20 years. Now, this gave us an opportunity to see what sort of data set was used by them to create models and train. And then we used them to see if we could also recreate models. So we are going to use the same data set for regression as well as classification. Only the target variable will be changed. So today, for this demonstration, we'll use the Freddie Mac dataset. We will not go much into data analysis and feature engineering because this has been covered in the second module. So I highly encourage you to go back and check out that if you haven't. We are going to train two models, a GLM, generalized linear model, and a GBM, gradient boosting machine, which is an ensemble, just to see how two different algorithms perform and which performs better. And then we're going to use our model to predict for unseen data. So let's get to the demo part. So this is supervised learning with H2O. I've already told you about H2O, the installation. So now what we're going to do is we are going to initiate an H2O cluster. So first we import this library, and after importing, we have to initiate a cluster. So that means we have to create a connection between our Python client and the H2O cluster, because again, it is a sort of a virtual, it's a JVM, Java virtual machine. And since we are doing it in Python and it's written in Java, so we need to create a connection between them. So a cluster is nothing but a group of nodes, and they work together. And when you submit a job to the cluster, it gets divided into all the nodes, and in a way, distributed processing takes place. And this makes the whole job very fast. So once I initiate this, I get all these parameters populated on my screen, which tell me the time zone of my cluster. And since I'm based out of India, so this is showing me my time zone. It is also showing me total number of cores and nodes. So I'm using it locally on my laptop. So it's showing me nodes, it's 1. It is also, it says that the Python version that I'm using, also the age of it. Now, I also get this line called checking whether there is an H2 instance running at localhost 54321. Now what this is if I click on this, this is the web UI, which is called H2O flow that opens up. Now what this is just an interface to H2O, and you can perform the same machine learning process here, but you don't have to code. You can simply click and do everything. This I will show you in the later part of the session. Now by default, H2O will use all the cores on your system. But if you don't want that, you can specify it here. And it has a lot of parameters which you can set. So right now n threads is -1, which means use all the cores, but you could specify. You could also specify the memory by going to maximum memory size. So by default, it uses 25% of the system's memory, but if your data set is big, you can accordingly define. So our objective is very clear. We have to predict whether or not a loan holder will default. So we're going to import the libraries, basic libraries like matplotlib to visualize the results, the estimators, because I told you we're going to use a GLM and a GBM, so we import those from H2O. And we'll also import H2O grid because we are going to do grid search to tune the hyperparameters. So I'll start by importing the data set. Now we can import the data set locally also if you've downloaded it on your system, or I'm currently importing it from AWS. And once I import it, I can actually see which are the different variables or the columns. So there are a lot of them. Now by default, if you give the head statement, head function, it will show you first 10 rows. Unlike pandas, if you must have used it, but you can specify the number of columns that you want to see. I'll just go to the end, and here is the delinquent column, which is of my interest, because this is something that I want to predict for anybody or a new person who will apply for loan in my bank. For instance, if I'm a data scientist there, and I have to predict whether he or she will default or not. So this is going to be my target column. Also, we can see some of the statistics of the data set by writing .describe, and this shows me that there are about 5 lakh rows and 27 columns. And this gives you quickly about mean, number of missing values, number of zeros, and so on. There's also a function called .table. So what .table does is, it will show you the distribution of any column. And since we are interested in the column delinquent, we only see the distribution of that column. And this shows us that the number of people who do not default are way too higher than the ones who default. So this is a classic example of an imbalanced, highly imbalanced data set where there's a big difference between the two categories that you're trying to predict. And why this is important is because having imbalanced data set will now define which metric you're going to use to actually measure the performance of your model. Now, we don't have a separate test and train data set, so we're going to utilize this data set, and we're going to split it into 3 parts: the validation part, the training part, the validation, and the testing part. I'm going to train my model on the training frame. I'm going to validate it on my validation frame, and I'll see if it's performing. If it's not performing well, I'll retrain it and retrain it. And then testing set is that set which I will not show my model at all, and will only be shown at the end of the experiment to finally see how my model is performing. So you only use the test data set once, but you can use the validation data set more than once to actually optimize the performance of your model. Now, I'm going to specify my target and predictor variables. So Y is my target variable, and this is delinquent. X is going to be all the others. But we have to make sure that we do not feed in those columns to the data set which are correlated to the target column. So over here, I'm going to ignore some of the columns. For instance, I'll ignore delinquent, obviously, because it is the target. I'm also going to ignore prepaid and prepayment penalty mortgage flag. Why am I ignoring this? Because this information is only got once the person has taken the loan. So you don't, if a person comes to a bank to take a loan, we don't know whether the person has already prepaid or not. So these two variables, if they're used for training the data set, will induce leakage in the data set. That is, information of the target variable will already be known, and then the whole process of training a data set is futile. So you have to make sure anytime you create a machine learning model, you have to be aware that you don't train your model on those variables which are correlated to your target variable. I'm also going to ignore the product type variable because this is a constant. Now I'm going to create a generalized linear model. So a generalized linear model is a family or a suite of models, and one of them is binomial. And I'm going to use binomial here because I have two classes to predict, true and false. I'm going to give a seed for reproducibility so that every time I get the same result, and I give a model ID. That is, I sort of give an ID to this so that anytime I have to fetch this model, I can just specify the model ID. And then we simply start training. So we'll write glm.train. We pass in our X, pass in our Y, we pass in our training frame where we want to train, and the validation frame. So now we have a GLM with us. So we've trained a GLM model. Now it's the time to actually see what are the metrics, how is it performing on the training set as well as on the validation set. So very good thing about H2O is it gives you detailed parameters, detailed history, scoring history, and you can see a complete summary of the model. So if you directly write GLM, firstly, you'll get some information about the model that you just trained, and we know it's a GLM. Then it will give me what was the metrics on the training data. So now I see that there are a lot of parameters or a lot of metrics here, MSE, RMSE, log loss. Now, which one shall I use? And why there are so many? And then what is this confusion matrix here? And I see similar ones for validation also. Now, quickly, I'll jump back to my slides to just give an overview to those who sort of want to understand why we use which metric to use when. So the default, so what I do is I'll create this 2x2 matrix. And what I do is this 2x2 matrix is called a confusion matrix, and I'll create a confusion matrix here. So what is a confusion matrix and why it is called confusion matrix? Because I can see the frequency with which a model confuses one label with the other. This is also called an error matrix. So let's say instead of 5 lakh samples, I am just going to use 1,000 samples for now. And let's say I got these results from my model. So for 850 people, I got this prediction to be true. So for these 850, they were true. That is, they defaulted on the model, and my machine learning model also predicted, yes, they will default. So that's true. That was actually the ground truth. For 70 people, these people did not default, and my model also predicted that they will not default. So this is also good. So these should be more because they are the correct ones. These are the correct predictions. For these 35, actually these people did not default, but my model predicted that they will default. Now this is something wrong. This was a wrong prediction by my model. And for this 45, actually they defaulted, and my model predicted that they will not default. Now, these two values, 35 and 45, are called type 1 error and type 2 error. And these are the errors that we need to minimize in our model. So the first thing that comes to your mind is to check the performance of a model. Let's use accuracy. We'll simply calculate the correct predictions and we'll divide by the total number of predictions. And yes, we can do that. And that comes out to be 92%, which is great. So we are very happy with our model and we say, yes, we've got 92% accuracy. Now, let's say you are working as a data scientist in a company and your manager comes up to you and tells you to create another model, similar model for fresh 1,000 batch of people. And what you do is you don't use machine learning. And what you simply do is you predict that yes, everybody will default. All 1,000 will default and you don't use any model. And then your manager checks the accuracy of your model. So what happens when you predict everything to be true? So 885 were actually true. And you also predicted it to be true. So that's okay. But for this 115, they were actually false. But you predicted it to be true. And now when you calculate the accuracy, it comes out to be 88.5%. It is lower than the previous one, but then you did not create any machine learning model. And it's just pure guessing. So, and this is not bad because you only have a difference of about 3.5%. So our model is only 3.5% better than using no model at all. And here accuracy is a misleading matrix and you cannot use accuracy in such cases because this is an imbalanced data set problem. So what's the alternative? What we can use? So the alternative is we can use precision or recall or F1 score depending upon the type of problem that we're trying to solve. So for instance, I'll again use the same confusion matrix, but now instead of putting the numbers, I'll put what they stand for. So if your predictions are actually positive and your model also predicts them to be positive, they are called true positives. Similarly, true negatives are the ones which are actually negative and your model also predicts them to be negative. So more the number of true positives and true negatives, better our model is, because this helps to differentiate between two classes as better as possible. Now FP is false positives. So these samples were actually negative, but your model predicted it to be positive. And FN are those samples which were actually positive, but your model predicted them to be negative. Again, we need to make sure that our model minimizes both FP and FN. That's false positives and false negatives. Now, how do you know? Now, both of them are interrelated. So the more false negatives you have in a model, the less false positives, and vice versa. Now, how do you know what you should do, whether you should minimize your false negatives or you should minimize your false positives? Now, this depends upon situation. If you see the current situation and say you're working for a hospital and you're supposed to create a model to identify whether a person has COVID-19 or not, in that case, false positives will be the ones who actually do not have the virus, but you predicted they will have the virus. So what will happen in such cases? Those people will be admitted to the hospital. Okay, which is not good. But imagine what happens if the reverse is true. If there are people who actually had the disease and your model predicted that they will not have the disease, it will be disastrous. So in such cases, false negatives are the crucial factor, and you need to make sure that you catch up all the people who had the virus. And when you have to do this, you will also have false positives, but then that's a trade-off. So this depends upon the problem at hand, and a lot of domain experience comes into play during this. So like I mentioned, you have other metrics like true positive rates or recall or sensitivity, specificity, and false positive rates, which are normally used for imbalanced problems. And we use AUC and ROC. So ROC curve is a curve which comes into play when you plot the true positive rates to the false positive rates. And these black dots, they represent the threshold values. Now, how threshold comes into play is a classification algorithm will always predict the probability. So, for instance, there is a patient and our algorithm says that there is 70% chance that this person has COVID and there's 30% chance that this person doesn't have COVID. Now you decide for a threshold. If your threshold is 50%, anybody having a probability of COVID of greater than 50% will be considered to be having the disease, and people with the probability of less than 50% will say they will not have the disease. But if you increase that threshold to 90, anybody with a probability of greater than 90% will be assumed to have the disease, and so on. So for every threshold, we create a different confusion matrix. But since we can have so many thresholds, creating so many confusion matrix will be actually confusing. And so we plot this curve, and these black dots represent those thresholds. And the area under this curve is called an AUC curve, area under the curve, and this determines how good your model is. So higher this curve, better is your model. And you could here, if there's a red and blue curve, these are two models. So the red curve is say for model 1 and the blue curve is for model 2, and the red curve will be a better model at prediction. So now, since we know all these metrics, let's get back to what we were doing. So now we know that we can use AUC in this case, and let's check the AUC. So AUC for validation is 0.8449. And this is the confusion matrix that I was talking about. This is the threshold that I was talking about. So from this summary, we saw that we focused on AUC, and we saw that for the training, it was 0.85, and for validation, it was 0.84. We can also plot our scoring history. And when we plot this, we see something that after probably 4 iterations, the performance isn't changing much. So we can choose 4. If you have to set the number of iterations, we can set it to 4, because there's no point actually in running the training process after 4 iterations. There's also a very interesting graph that we can plot called variable importance. And this shows us which variable contributes the maximum in the predictions. And here it is servicer name Wells Fargo Bank. The second is also servicer name, third is also. So this gives an idea this variable servicer name is important. Now, not generally that it is always very important for Wells Fargo, but this in itself, servicer name is important when you're making these predictions. Now let's predict for a validation set, and we make predictions for our first 10 values. And let's see here. So we've just combined our predictions with the data frame to compare them. And we see that, and we use the head function to see the top 10. So we see here that for every prediction it's saying false, except this prediction where it says true. Now, why is it saying true here? These are the probabilities. So for this value, the probability that it will be false is 99%, whereas the probability that it will be true is 0.5%. Hence, this is classified as false. So there must be some threshold which is deciding this. And let's go back. And Here we find the threshold 0.122396. So this means that any value which will be greater than 0.1224 will be predicted as true. And for only this satisfies this condition because it has a probability of 0.3, which is greater than 0.1224. So it is this way that thresholds are used to actually determine whether a sample will be predicted false, true, yes, no, etc. So we've trained our GLM model and it's performing fairly well. 0.8449 is the AUC. So can we perform even better? You can also, if you want to go check, you can go to this link and you can check the whole documentation of the GLM model and the entire family. So can we do it? Yes, we can. We can tune our models. And what do you mean by tuning the models? So there are two aspects of a model. A model has a parameter and it has an hyperparameter. So a parameter of a model is a variable whose value is estimated from the data set. So it learns from the data set, it gets trained. And parameters are those values which a model learns during the training. For example, weights. So how much weight is to be assigned to which variable? You cannot set them manually because this is something that the model will learn over time. Hyperparameter, on the other hand, are those parameters which need to be defined even before the training starts. So for instance, if you use a decision tree, you need to define number of, if you use a random forest, you can define the number of leaves or the depth, etc. So this has to be set before even you start the training. Now, how do you know which hyperparameter to set? Which depth will give the best performance? So there are ways in which you can optimize them. Either you can set them manually, but manually, how many times will you try? It'll be just iterations. What else you can do is you can use hyperparameter tuning options. And there are a lot of them available, but in H2O, we have two. So we have Cartesian grid search and random grid search. So what do you mean by a Cartesian grid search? So for Cartesian grid search, our algorithm, our tuning algorithm will actually go and will start searching for every parameter that we have mentioned. So for instance, you specify a set of each hyperparameter that you wanted to search over. And H2 will train a model for every combination of that value. So if you have 3 hyperparameters values and you specify, say, 5 for one, 10 for the other, and 2 for the third one, so the total number of models will be 5 into 10 into 2, that is 100. So your H2 will create 100 models for it because it is going to try every possible combination of those 3 hyperparameters. Now, this is going to take a lot of time as well as memory. There's another way of doing that, and that is by random grid search. So a random grid search, instead of specifying every value, you just give it a boundary. And you say you will search in this boundary, like from 10, 20, 30, 40, and so it searches for the parameters in that boundary. And since it does that randomly, it's faster. And you can use either of the two, but today I'll just demonstrate the random grid search because again, it is faster. So it's very similar to like we trained our GLM model. First, we are going to define our model. So, but we're going to use h2o.grid.h2 grid search. We're going to put in our GLM model, H2O generalized linear estimator, and similarly the family. Then we're going to put our hyperparameters. So you have alpha, you have missing value handling, and then the search criteria. So alpha is the distribution of regularization, which means regularization is a way to reduce the overfitting in your machine learning models. You want your models to generalize well on unseen data and not to learn things. So that is alpha. Lambda is your regularization strength. And missing values handling this allows you to, it tells H2O how it wants to handle the missing data. So you want to skip the missing data, or you want to imputate it using mean, all those things. So you can go back to the documentation. This might seem to be a little fast because seeing the time, but if you go to the documentation, this has been very nicely explained. And once you just go through here right now, you'll be able to catch up very fast. So I put my criteria and I put the maximum models that I wanted to train, and I want the maximum runtime because I don't want it to go forever. You can specify whatever you want here, depending upon the time in the computer that you have. And then it runs, will again train the model again. And then we get a leaderboard. Now this tells you that for this value of alpha and for skipping the missing values, it gets the maximum AUC. And this actually shows you the number of tries that it did. And it says that this is the best combination of hyperparameters that it has got. And this is way better than vanilla GLM that you did, because now if you compare both of your models here, so the default GLM gave you 0.8450, whereas the tuned GLM gave you 0.85. Now this improvement may not be much, but this is just a linear model, and if you're going to use some advanced models and ensembles, this will be even better. So this was generalized linear model, which is a linear model like a logistic regression. If we were to use a GBM, a gradient boosting machine, which is an ensemble and a sequential ensemble, because it builds upon, it improves the results of the previous model. So it's you could say it's a sequential ensemble of random forests, and it builds upon and it improves the weaknesses of the previous trees. You're going to do the same process for this, which is exactly the same. You're going to create a model first. You'll see the summary of the model. You are going to then tune your model, and then you're going to compare the result. And again, you can see for default GBM, we got an AUC of 0.85, whereas for tune, we got 0.86. You can now test it on your test set, which you had actually kept unseen, hold out, and you see that your GBM performs better than your GLM. And once you do your whole modeling process, you've also made predictions, make sure that you shut down your H2O cluster. So this is the way in which you typically use H2O. This remains pretty much same for a regression also, except that you will change your algorithm, and you will also change the target variable. So let's quickly, I'll show you how you can do the regression part of it. But before that, I'll quickly go over the problem that we're going to try to solve for regression. And because it's regression and you have to predict some continuous variable, we are going to predict the interest rate for a loan. So what is going to be the interest rate? 5, 6, 7%. And for this specific case, we are going to use H2O's XGBoost model. Now, why would we want to use H2O's XGBoost model and not the XGBoost that's available? Because XGBoost is also available, which has been created by them. It's because H2O's XGBoost gives you the capabilities of H2O. For instance, like data preparation, and also all the other aspects, like you can, so because XGBoost only works with numbers, but H2O can actually handle categorical variables, so you get this additional advantage. Now for regression, because it's typically the same in a Jupyter notebook, what I will show is how to use it in the web UI. which is called flow. Now, how do you access this? So you will initiate a cluster, and when you initiate the cluster, you get a bunch of information, and you just need to go to this link. And when you go to that link, you get access to H2O flow. Now, H2O flow is very intuitive, and you need to first import a data set. So under assistance also tells you how to do stuff, but you can go here on the top and you can just import files or SQL table, or you can even upload files. And I've already uploaded it because I was not sure if it'll take more time. So once you import your file, you have to parse those files. So I have imported the same data set that I was using before, and this data set has these many columns, and I'll just parse them to get them into H2O's memory. And this parsing in H2O is very, very fast. Now let's just look at the data set that we have. So a data set has this loan level data set, and it has like credit score, the first payment date, and maturity date. But something of our interest is this original interest rate that we want to predict. And there's something very interesting about H2O is that the data types are int for integers, real for real numbers, and enum for categorical variables. So here you have enum. So if you encounter this, this is not some error, but this is something which is with H2O, and we categorize categoricals as enum. So we've seen our data set. Now the next thing would be to split the data set. So I'll again go to data set, and I'll split my frame, and I'll select the frame. And so I'm going to split it into 3 parts. So it's going to be 75, 15, and 10. And I'll just name them so that I know what they stand for. This is the train set. This is the validation set. And third one is going to be my test set. And I'll create. So now I have 3 frames that I have created. Next, I think I will use one of the models. So I have a lot of models that you can see, but right now I'm only interested in XGBoost. Now, as soon as you click on that model, you get a lot of parameters that you can put in. And this is so intuitive because instead of going back to documentation and seeing how many parameters are available, you can directly see here. And you can just go on putting it. So the training frame that I'm going to use is the train. The validation frame that I'm going to use is the valid. And do you want n folds? And n folds are the number of folds for cross-validation. If you want, you can put them. If you don't want, you don't need to. You need to specify a response column. So this is going to be the interest rate, this one. Of course, you want to ignore few columns, just like we did before. And you need to select the ones that you want to remove. So firstly, of course, I'll want to remove this specific model that the variable or the target variable, that is original interest rate. But I cannot find it here. So because I need to click the next 10. So before that, I will also remove first payment date. I'll remove the maturity date. I'll remove the mortgage insurance. Then I'll go to the next 10, and I'm going to remove the original interest rate also, because of course I don't want it to be repeated in both my training and testing data sets. And then I can go and train my model. Now you can see there are all other parameters also. So just for the time, I'm just going to reduce the number of trees to 10 because I want it to just go faster. And I'm just going to leave it as it is, and I will build my model. So it says that my model has some errors. So, okay, so now there's an error here. It says validation frame must have response column original interest rate. So if you want to check, I can go and check on my validation frame. And this is my validation frame. So it says that it does have original interest rate. Okay, so it did not find it in this. So I might have to import this data set again, and I'll just parse it again. Okay, I'll view this data set again. And does it have this? Yes, it does have original interest rate. And then I'm going to split my data set again. And let's just, in the interest of the time, I just use 2 this time to split it into a training and a validation set. I create my 2 set, and I'll create a model. I'll use my training set. I'll use my validation set. And I'll choose my column, and this is going to be original interest rate. Okay, so now it's building, and it's very fast, and it's already built our model. It has trained a model. And now we can very nicely see the summary. So here what you see is this graph. So this is basically your training and your validation. Now they are appearing to be overlapped because they're pretty similar. And this is the training deviance and validation deviance with respect to the number of trees that you have. From here, you can also see your variable importance. You can also see your model summary, number of trees you've used. Again, you can see the variable importance in the form of a table. And you can now predict. You can predict it on an unseen data set. For instance, on a validation data set, you can directly predict and you get the results. So this is the results that you've got for the validation data set. Another nice thing here is you can download the Mojo or the model deployment package, and then you can use it and use in a production environment. You can click on this and this starts downloading. So you can also export it, and you can do a lot of things with this. Now, how about model tuning? How do we tune in case of flow? So tuning is nothing but setting up your hyperparameters. So here we have all those parameters, and we can just click from here and choose what sort of parameter we want. Like normalized type should be tree or forest. Booster should be GB tree, GB linear, dart. So the best part here is you have the summary of what that feature does, and you can then simply put it in these values. And then you can again retrain your model. So this is flow, and this just replicates what you did in your Jupyter notebooks, but you don't have to code, you just can simply click. And there is also a water meter that you have, which basically shows you how your model is working. So each bar, blue bar here, represents a CPU. And when you are training your model, you can see that all of your CPUs are engaged, thereby showing that how H2O helps in distributed processing and multi-threading, multi-core. So this was about the supervised classification in H2O, regression and classification. Of course, you will have to go back to the documentation and read it. It's written very nicely. You can just replicate a few examples. And if you have examples, you use scikit-learn, you can replicate them using H2O. For the upcoming session, session 2 of this module is automated machine learning with H2O driverless AI. So that is the automated enterprise version. And we're going to use the same classification regression in driverless AI. And we are going to have Philip with us. Philip is a Kaggle grandmaster, a Kaggle competitions grandmaster. Kaggle is basically a platform having more than 5 million data scientists who work towards solving machine learning problems. He is currently ranked number 5, and he has been sort of winning a lot of competitions, and it'll be great for you to interact with him and ask him questions. So he'll be taking that session on 24th. And again, there's going to be a study group and AMA session where you can ask your doubts pertaining to the session and anything relates to H2O-3. So for the resources, there's the glossary where all the metrics, etc., are placed there. You can understand about downloading H2O, supervised learning, how's the H2O architecture based, and you can also go and check out the other algorithms which are available in H2O suite. So that's all from me. Now.
Thank you, Parul. We have we have one question. Do you see the question, or do you want me to read it to you?
Let me see. There are questions in Zoom webinar chat also, and there are also questions in the questions tab.
I would look at the Q&A.
Let me just first stop sharing my screen. Okay, so what is meant by deviance? Deviance is how much is your prediction away from the actual value. So if your actual value is, say, the interest, say, is 9%, and your value is about 7%, so we're going to say your predicted value is at 2% deviates from your actual value. So it could be on the positive side also, it could be on the negative side also.
Yeah, there's a question about using flow in Aquarium. So I think at the moment we've been having some security concerns around in Aquarium. So I think you will have to install I think H2O locally. The instructions for the tutorials have been updated so you can install H2O and flow locally and run it locally. There's also a question, Parul, around, is driverless AI a superset of H2O-3? And also, does it also use it?
So, see, H2O and driverless AI are, I think, completely different aspects. And just because they're from the same company doesn't mean that, one has to be a superset or a subset of the other. H2O is an open source platform. It's sort of a library, actually, of algorithms. And driverless AI uses a lot of other things under the hood, Pi data table, and it does not necessarily uses H2 for the algorithms. It uses TensorFlow, it uses PyTorch. So they're two different, you could say, mechanisms for solving machine learning problems.
Yeah, I think the other thing is it can use H2O-3.
Yes, it can.
Yeah, and then H2O-3 can work on your single machine laptop and can scale to sort of a cluster. Driverless AI is really a server-oriented software, and it works on one machine, right? So it's not a distributed sort of approach. And there's some integration that's in the work progress that kind of scale up driverless even further and kind of do further integration back and forth between H2O-3 and driverless.
So there's another question that I can see is, are some models better at handling unbalanced data sets? Yes, your tree-based algorithms are definitely better for handling unbalanced data set. So most often than not, a lot of people, when they start working, it's the tree family algorithms that are used. The GLMs are not that good in handling unbalanced data sets.
Okay, seems like those are the questions. So thanks everybody for joining. Remember, this is a 4-part, there's 4 sessions in this series. So, please tune back on Thursday, and we will be diving deeper into automatic machine learning with driverless AI, and maybe you'll get a better sense of sort of some of the differences as you kind of dig into it and get hands-on with that. So thank you very much, Parul, and thank everyone for joining, and I hope to see you in our next session on Thursday. Have a good day. Bye-bye.